Good afternoon, everyone. Our presentation today will be on a holistic approach for protection of storage tank bottoms against soil site corrosion. In this webinar, we will shed light on some of the most common causes of soil site corrosion, introduce vapor phase corrosion inhibitor system solution in terms of working mechanism, the system components, and how it's applied. We will also share with you case studies that demonstrate the long-term performance of VCI solution against soil site corrosion and how it contributes to the overall protection of the storage tank. And we will conclude our webinar with an update on the position of VCI technology for soil site corrosion on storage tank bottoms in the international standards arena. It's important as a start to remind ourselves of the significance of the soil site corrosion problem for above ground storage tanks. We all know it's a principal cause of storage tank failure, as it leads to plate thickness loss, holes in the tank floor, and eventually leaks, which impose major environmental risks and operational challenges to tank owners, operators, who always aim to find an effective control method for this type of corrosion during the complete life cycle of the tank. To translate the significance of the problems into numbers, this is a study done by an asset integrity company, Inventure Technologies, for 4 terminals, for 142 tanks in 4 terminals in the Middle East. And in both graphs that you can see on the screen, the y-axis is the corrosion rate value in millimeter, and the x-axis is the tank number. The graph at the top shows the highest corrosion rate in the sketch and central plates of each tank, and the graph at the bottom shows the highest corrosion rate in the annular plates of each tank. Both graphs show that basically the corrosion rate in the central and the annular plates are as high as 1.2 millimeter per year, which means tanks that are corroding at this rate will leak in less than 6 years from commissioning date. Now, the soil site corrosion directly impacts the service life of the tank. So from the previous slide, we saw that the corrosion rate can go as high as 1 and 1.2 millimeter per year. And then when you have high corrosion rate, this impacts the service life of the tanks. In these 2 graphs, the y-axis is the tank service life in years, and the x-axis is the tank number, sorted in ascending order based on the service life value. The top graph shows that 15% of the tanks got rejected due to corrosion in the sketch and the central plates with 10 years from commissioning, and 35% within 20 years. The bottom graph shows that 11% of the tanks were taken out of service before the scheduled inspection due to leaks in the annular plates. So you can imagine the impact on the operation and basically on the operations of the terminals or in the refineries where tanks exist. Now, when soil site corrosion impacts the service life, it increases the operation cost of the tank, which is both a combination of direct cost, which is repair costs and all the costs associated with the inspection when the tank is out of service, and the revenue loss due to the downtime. So, for example, tank number 43, towards the end of the graph, cost the owner $1.3 million in repair costs, and almost $1 million because the tank was out of service for maintenance for a long period of time, for the duration of the inspection. And this is where protecting the tank bottom and basically using, for example, the case of protecting it using VCI technology, can add value to the clients by minimizing on the tank, maximizing on the tank performance and minimizing the probability of failure due to soil site corrosion, and basically rendering the OPEX related to the tank floor inspection and repair and maintenance as low as possible. There have been several methods adopted to mitigate soil site corrosion on above ground storage tanks over many years. Some examples are the use of bituminous sand or oily sand layer, impressed current cathodic protection, and coatings also to basically minimize and reduce the corrosion, soil site corrosion. However, total effectiveness of these techniques as a standalone or combined have been questionable in providing the required protection against soil site corrosion. And this is, in many cases when the tank owners take the tank out of service, they scan the floor, they see there is an active soil site corrosion. For example, in case of using oily sand or bituminous layer, according to the literature, there are several technical papers published on this issue, where the bituminous layer proved to be basically, or trap the moisture and the corrosive species between the underside of the tank floor and the construction pad, resulting sometimes in creating a corrosive environment. One contributor, and a main one, to soil site corrosion is the presence of gaps between the annular plates and the tank ring wall. Such gaps allow the ingress of moisture, rainwater, fire sprinkler or tank deluge systems, creating water pooling and ponding around the base and around the base of the tank. And also the gap allows for the diffusion of airborne chlorides, especially for facilities that are located in coastal areas where airborne chlorides and other corrosive ions can diffuse from the outer environment or the ambient atmosphere or the surrounding environment into the under tank environment. It's, at least I can speak with great confidence that it's not unusual for tank owners in the Middle East, at least, to have the underside of the tank bottom plates coated during construction. However, due to unavoidable defects during coating application and handling of the bottom plates, creates pinholes, scratches, and also thermal damage during the welding of the bottom plates, and also the natural deterioration or aging of the coating during the tank operation. We're talking about usually the design life of the tank or service life of the tank is between 20 to 30 years. Coating deteriorates much faster than that. So it's widely accepted that coating of bottom plates alone cannot prevent soil site corrosion. The presence of, this is in case of tank owners utilize cathodic protection for protecting the tank bottom plates against soil site corrosion. The presence of shielding material, or even like the inevitable air gaps that are because of the canning effect, filling and refilling cycle, or because of the presence of settlement in the tank pad, doesn't allow the CP current to reach to the underside of the tank floor and polarize the structure to the protective potential. Also, in case of using clean sand, sand with time dries, and when it dries, it increases the basically the its resistivity and reduces the amount of current reaching to the tank bottom plates and to provide the required protection. It's not to mention that in the presence of bitumen layer or oily sand layer, this kind of material works as an insulator for cathodic protection. So an API 651, for example, discourages the combination of cathodic protection um, and bitumen layer or oily sand layer, because it reduces or insulates or shields the CP current from reaching to the tank floor. We all know that there are always overlap because of the weld joints. This is also areas where CP current cannot reach. At the interface between the ring wall and the annular plates, these areas, again, cathodic protection cannot reach. So these are areas where cathodic protection can fail to provide the required protection. Now, one solution that has been applied for the last 20 years, and they're getting more and more momentum and acceptance in the industry, is the use of vapor phase corrosion inhibitors to provide protection for the tank floor and also supplement, for example, the cathodic protection in the areas where it doesn't provide the required protection. So vapor phase corrosion inhibitor solution is an engineered solution to mitigate soil site corrosion on storage tank bottoms, and it's typically composed of 3 or 4 main components. The first component is the volatile corrosion inhibitor material, which can be in the form of powder or slurry, as we will see, depending on the application methodology. It's introduced under the tank, and we will see how this material can be introduced under the tank depending on the tank status, whether it's in service or out of service. The second component is the monitoring system. So we introduce a corrosion monitoring system to monitor the corrosion before and after the introduction of the vapor phase corrosion inhibitor material. And the third component is a chime area seal system to close the gap between the annular plates and the ring wall. The fourth one is basically the delivery system on how you can introduce the vapor phase corrosion inhibitor slurry or liquid or the powder. So these are the main components of an engineered system, and you can see that we're looking at closing the gap, monitoring the corrosion, and applying an active basically corrosion protection method, which is the vapor phase corrosion inhibitor. Now, the first component, which is the vapor phase corrosion inhibitors, they provide protection against soil site corrosion. They can provide protection for coated surfaces and previously corroded steel. They are basically organic salts, mixtures of amines and carboxylic acids. They come in the form of, as I mentioned in the previous slide, powder or liquid slurry, and they are environmentally safe and do not contain nitrates or other harmful chemicals. Once the VPCI material is introduced under the tank bottom plates, it vaporizes, diffuses through the sand and spaces, reach to the underside of the tank bottom plates, absorb onto the surface, and form a monomolecular protective layer on the plates that are in contact with the tank pad and in the air gap areas where the CP current, for example, cannot reach. So it provides you with a comprehensive protection. That's the working mechanism of the vapor phase corrosion inhibitors. The second component is of the engineered solution is the monitoring system, which uses corrosion probes such as electrical resistance probes. Multiple probes, depending on the size of the tank, are installed by core drilling through the ring wall, pushing a PVC tube under the tank and inserting the probes under the tank foundation through the slotted PVC tubes. Probes are usually installed 2 to 8 weeks before injection of the VCI material to create a corrosion rate baseline. Once the baseline corrosion rate is established, a suitable corrosion inhibitor material will be injected, and the corrosion monitoring continues to be monitored, showing a reduction in the corrosion rate over time. one of the requirements to maximize on the service life of the vapor phase corrosion inhibitor solution and the protection of the tank in general is to have a sound chime area seal system, which prevents the ingress of, as I mentioned previously, water, moisture, oxygen, and also help contain the vapor phase corrosion inhibitors under the tank. Tank chime area seal system usually is composed of a backer rod used in the usually gaps that are greater than 10 mm, a sealant, viscoelastic sealant, a wrapping band, and a top coat to provide protection for the wrapping band against basically UV rays and the degradation because of the exposure to the atmospheric conditions over time. So this is the engineered system and the different components of the system. Now we will be talking about application methodologies, the most common application methodologies for introducing vapor phase corrosion inhibitors under the tank. The first application methodology is basically is through the tank floor. This application method is done when the tank, as it implies, when the tank is out of service for inspection, and it's applicable for tank foundation types, for all types of foundations. So tanks constructed on oily sand, bitumen sand, clean sand, continuous concrete slab. This approach or application methodology is applicable to all types of tank pads, and it's also more resilient to tank foundations that are without release preventive barrier compared to the other application method that I will discuss in the next slides. So that's the through tank floor. That's the first application methodology, and this is an animation that shows how the powder is applied under the tank, where basically after the installation of the corrosion probes that we saw previously and establishing the corrosion rate baseline, we drill holes, number of holes, into the tank floor, and then we basically add the powder into a pneumatic machine and fog the powder through the hole drilled into the tank floor, and then we patch weld the hole, and then once the powder trapped under the tank floor, it starts to sublimate, and then it releases the protective molecules and provides the protection against soil site corrosion and suppress the active corrosion rate onto the tank floor. And with the use of the corrosion monitoring probes, you can see the effect and the reduction in the corrosion rate with time. The second application methodology is the through ring wall application, and this application methodology is applicable for tanks specifically constructed on ring wall, or ring wall, whether it's concrete ring wall or crushed stone ring wall, with clean sand, because again, the presence of oily sand or the presence of asphalt may reduce the diffusion of the VPCI if injected underneath these layers to minimum, because the diffusion rate of vapor phase corrosion inhibitors through such layers are very low. And in this case, if you have a wash sand and a ring wall with release preventive barriers, that's the ideal tank foundation configuration for this application. And we use basically vapor phase corrosion inhibitor liquid in the form of a slurry. This is an animation that shows how the application methodology is done. We core drill into the ring wall, we push perforated PVC tubes all the way to the center of the tank, and then inject the vapor phase corrosion inhibitor liquid into the sand pad, and again the liquid will diffuse through the sand, reach to the underside of the tank floor, absorb the vapor phase corrosion inhibitor molecules will absorb onto the surface, and then form this protective layer, again suppressing active corrosion rate on the tank bottom plates surface. In the next section, we will share with you some case studies that where the vapor phase corrosion inhibitor solution was utilized. The first case study is for a crude oil tank, 104 meters in diameter, for a major oil and gas operating company in the region, in the Gulf region. The tank is, as I said, crude oil tank, 104 meters in diameter, constructed on an oily sand layer with impressed current cathodic protection system, also distributed system. It was taken out of service in 2010. You can see the result of the MFL floor scan showing areas with high metal loss reduction. Probes were installed around the tank about 60 days before injection, and then vapor phase corrosion inhibitor powder was injected through the temporary injection ports, and then the corrosion rate was monitored for 36 months. And you can see the difference between the corrosion rate before and after, and with a percentage reduction of an average of 92% reduction on the corrosion probes. The second case study is for a fire water tank in a basically saline water conversion or desalination plant. It's online, where the vapor phase corrosion inhibitor liquid or slurry was injected through 3 injectors. The injectors are basically the black solid arrows, and 3 probes were installed also under the tank, which you can see indicated by the dotted or dashed red arrows. The CP system for this tank was not functioning because of a cut in the power in one of the joints under the tank, and retrofitting the existing cathodic protection system is very time consuming and costly. And at the same time, this is a fire water tank where the facility owner cannot keep the facility without it's related to the safety of the facility. So they decided to provide protection using vapor phase corrosion inhibitor technology, and these are basically the results. You have 3 probes that showed a percentage reduction of an average of 90% on the corrosion rate measured by the probes before and after the injection. So the first 2 case studies showed the performance of the vapor phase corrosion inhibitor based on corrosion monitoring probes. In the next 2 case studies, I will share with you results based on tank floor scan data. So to demonstrate the effect of vapor phase corrosion inhibitor solution on tank integrity and on the tank integrity and inspection results, tank floor scan data was compared before and after application of the vapor phase corrosion inhibitor solution. The first case study is for a tank in a storage terminal in the GCC country. It's 38 meters in diameter tank constructed in 2010 on crushed stone ring wall, clean sand, HDPE, and with a release preventive barrier. The tank leaked after 6 years from construction date. So in 2016, the tank leaked, and it had to be taken out of service for inspection and repair. In 2020, the tank owner needed to change the service or the product stored in the tank, so they had to take the tank out of service, and they took this as an opportunity to check the floor status after implementing our solution in 2016. So this is the tank floor condition in 2016, which revealed, the tank floor scan revealed severe soil site corrosion up to 1.17 millimeter per year corrosion rate, with several plates with through holes and more than 80 locations having less than 6 mm thickness. Based on the tank floor inspection activities, a repair plan was prepared to fully replace the annular plates. And the repair plan included replacement of 30 sketch plates, replacing all the annular plates, replacing 30 sketch plates, and placing 58 welded-on patch plates, and inject VPCI powder at that time. So, but before taking into consideration the effect of vapor phase corrosion inhibitor, a risk assessment study was done, and it showed that the calculated corrosion rate after the repair is 0.24 millimeter per year, and this is definitely for the unrepaired areas. And the next inspection interval will be less than 9 years based on the risk assessment. Now, vapor phase corrosion inhibitor powder was introduced, and this is the result after 4 years of the tank floor. So when they decided to take the tank out of service to change the product stored in the tank, they also took this as a chance to scan the floor, and basically the scan showed an 86% reduction in the corrosion rate from 0.034 MPY to from 0.24 millimeter per year to 0.034 millimeter per year, which is an 86% reduction. The tank was did not require any repair at that time, and it was boxed up, and it was good to go for another 10 years. Another study is for a 6-year study for a sour water tank, 29 meters in diameter, located in a refinery in one of the GCC countries. The tank was constructed in 2005 on a concrete ring wall with clean sand also, with cathodic protection and HDPE or release preventive barrier. The tank leaked in 2010, so we're talking about 5 years from commissioning date, and was taken out of service for inspection and repair back then in 2010. After 3 years, the tank leaked again and was taken out of service. It's a severe case, and it was taken out of service for inspection again. At that time, the tank owner decided that they want to go ahead and change the entire tank floor area, but that's from the inspection and perspective. But the operations preferred if they can put the tank back in service and find a solution just to help them meet the scheduled next inspection. So and this is where they thought about utilizing vapor phase corrosion inhibitor to help them just keep the tank in service without replacing the entire tank floor, do the repair, the patch repair, and just help them keep the tank in service for the scheduled T&I, which was in 2019. So they utilized the vapor phase corrosion inhibitor, and they basically they did that, and these are the findings from the inspection in 2013. So the main findings were they had more than 40% thickness loss in 28 out of 40 membrane plates, 5 annular plates with perforations out of 16 plates. Repair plan was again developed based on the findings, and based on the patch repair plan, and the risk assessment that was done based on the patch repair plan, the tank would do only 3 years without introducing any corrosion protection method. The risk assessment shows that the tank needs to be taken out of service in 3 years' time to avoid any failure. So we went ahead and introduced the vapor phase corrosion inhibitors, which reduces the active corrosion rate, and reduces, in this case, the probability of failure, and it can help you extend the next inspection interval. And that's what happened. After injection of the tank with vapor phase corrosion inhibitor powder, the tank was boxed up and in 2013, and it was opened in 2019. Since the main objective of the tank owner was to avoid any tank leak with minimal repair for the next 6 years, this objective was achieved, and the decision to replace the entire tank floor in 2019 was already taken in 2013. They just wanted, to keep the tank with minimal repairs back then until it reaches 2019. The tank owner opted just only to scan 40% of the tank area in 2019. That's why you can see on the floor scan that it's not for the entire tank. They only scanned 40% of the tank, just I would say a sanity check to see if there was an effect from the corrosion rate or not, from the vapor phase corrosion inhibitor or not, and the partially scanned area shows that vapor phase corrosion inhibitor helped reduce the corrosion rate by 43%. And the tank did not leak during its service life. A more comprehensive case study was done on 12 tanks, which had basically, this is a NACE paper that shows a summary of a study done on 12 tanks that had, what's really special about the study is that the 12 tanks had new floors, all of them, new floors. So you have a clear baseline of the starting point. 5 tanks of the 12 tanks were protected with vapor phase corrosion inhibitors, and 7 tanks were protected with cathodic protection. And the tanks were later inspected as per the Schedule T&I, and between 7 to 10 years for the 12 tanks. And the MFL floor scan data findings, they are summarized in the graph that you can see on the screen that plots the total number of corrosion indications per the magnitude of corrosion rate. So the blue data is for the CP protected tanks, and the yellow data is for the vapor phase corrosion inhibitor protected tanks. And you can see that the vapor phase corrosion inhibitors have shown very good long-term performance compared to the cathodic protection. This is the slide where it shows the evolution or the adoption of the vapor phase corrosion inhibitor on the international standards or the industry standards. So the ever-increasing deployment of this technology in the field has been reflected through recognition of environmental protection agencies, government regulatory bodies, and international associations. We're talking about 20 years. So in 2003, the Department, for example, of Environmental Protection in Florida approved the use of vapor phase corrosion inhibitors of tanks for tanks where the cathodic protection retrofits are infeasible. It was conditional approval. 10 years later, the state of Florida identified that vapor phase corrosion inhibitor can be used in tandem with CP or standalone solution. So because of the track record from 2003 to 2013, it gave the confidence that this solution can be used as a standalone or in combination with cathodic protection. 8 years later, in 2018, API published the standard the revision of 2610, which is the tanks and terminals standard, outlined the use of BCI for the tank bottom in section 12.5. API, a technical report was published by API in 2021, so April last year. API Technical Report 655, it provides detail on utilizing volatile corrosion inhibitors for protection of the soil side of tank bottoms. And also AMP, which is formerly known as NACE, There is another standard that is being completed by the task group 543, which is a comprehensive document on the protection of protection of tank floors against soil side corrosion, and it also provides details on the utilization of vapor phase corrosion inhibitors for protection against soil side corrosion. So, in brief, vapor phase corrosion inhibitors application can help tank owners switch from time-based inspection to risk-based inspection. It can also and may help in deferring a scheduled out-of-service inspection safely when needed. It can contribute to the extension in the next inspection interval, and also can help increase the overall service life and reduce the storage tank OPEX by 30%. So that's it from my side. How did I do, Kenna, with the time?